So today's topic is moment of inertia. Let's just start with the word term inertia. From the Newton's first law of motion, we know that if the body in motion tries to stay in motion, and if the object is at the rest, it will try to remain at the rest. So basically, object is trying to maintain its state of motion, which either it can be at rest or either it can be at the motion. Now, how object will resist or how much object will resist is defined by the inertia. And inertia is basically mass of the object. If the object has higher mass, it has higher inertia, and higher will be the resistance of the object to the change in motion. But this only applies to the linear motion. What will happen if object is at the rotational motion? How much object will resist? And that the resistance is defined by the moment of inertia. And it is equivalent of mass. Like how much the mass will resist in the linear motion, there is equivalency of moment of inertia that will resist the change in the rotational motion, and we will prove that. So let's just start with a rigid object made up of the n number of particles which are situated throughout the object. So this will be the axis of rotation for that object. And let's just say there is a particle at r1 distance, there is a particle at r2 distance, and so on and so forth. So now there will be n1, n2 up to n number of particles, and then their mass will be, mass will be m1, m2 up to mn, and they will be at the distance r1, r2 and so on up to rn. Now we can individually give the kinetic energy to each and every particle, such as kinetic energy of the first particle will be half m v1 square, and kinetic energy 2 will be half m v2 square, and overall kinetic energy of all the particles will be summation of this individual kinetic energy. So your kinetic energy will be half m1 v1 square plus half m2 v2 square up to half mn vn square. So here we can write it as summation of mn, mi, I goes from 1 to n, vi square. So here we can put the value of v as r omega. So half mi ri square omega square. I will go from 1 to n. And here we will define summation mi ri square. We will put mi ri square as I, where I will be your moment of inertia. And your kinetic energy will be half I omega square. So from here we can say that as we have formula of kinetic energy is half mv square. So here v is in rotational motion, v is being replaced by omega and m is replaced by I. So from here we can evidently say that as there is mass for the inertia in the linear motion, I is for the inertia, I is the moment of inertia, I is for the rotational motion. And here how much bigger the I is, how much bigger the moment of inertia of the object is, it will be harder to rotate that object. If object has smaller moment of inertia, it will be easier to rotate that object. If object has higher moment of inertia, there will be much larger force will be required to rotate that object. And here we have considered object to be made up of small individual particles, small finite number of particles, which is object made up of. But for the practical reason, we consider it as where your dm will be the individual mass, that small mass component of that object, and r will be r will be distance from axis of rotation. Now, what if we have considered a random object, but what if we have a defined shaped object, like let's just say a ring? So, what will be the moment of inertia of a ring? If we consider a ring and there is a axis passing from the center of the ring. Now from this formula where we defined I is equal to integration of r square dm. Now here r is the distance from the axis of rotation. So here small r will be equal to the capital R, which is radius of a ring, and here dm, as it is a uniform ring, the mass of the ring is uniformly distributed along its axis, along the ring, and therefore we can consider our dm to be a small element of that ring. And here we will have a formula which will be equal to, as r is constant, it will be outside integration, and we will have dm, and integration of that dm will be your total mass, which is m. So I of ring is equal to m r square. This will be a formula for your moment of inertia of a ring. Now here we can say that if the axis is passing through the center, the moment of inertia will only depend on the mass. Like higher will be the mass of the ring, we will have the difficulty in rotating that ring. Now we can just go beyond the ring and a step further from the ring and have a much difficulter problem than a ring. We can take a disc and we can find out what will be the moment of inertia for the disc. But this trick of dm will not work for the disc. So when we talk about the disc, we will consider a disc which will have a uniform mass density. We will define sigma as mass density of a disc. Sigma will be mass by area, or we can keep it as mass will be equal to sigma by r square. Here we can again jump to our original formula where I is equal to integration of r square dm, and your mass element will be, your small mass element will be sigma by r square, or we can take its derivative, which will be equal to 2 sigma by r. So here we will have integration of 2 sigma by r square dr. 2 sigma and pi are constant, and we will have integration of r cube dr. So this integration will be r square r raised to 4 divided by from 0 to r. I can take sigma I can take sigma, pi and r square to one side, combine them, and we can have r square upon 2 to the other end. And this we can define as, this term we can again from our, let's say, equation 1, we can put it as capital M, which will be the mass of the entire disk, and we will have the moment of inertia for the disk, which will be m r square by 2. So from these two examples, we have defined the moment of inertia of the two symmetric, perfectly uniform objects. By doing such calculations, we can also do the moment of inertia for the various objects such as sphere, such as cylinder, that we will see.